हेलो फ्रेंड, वेलकम टू ब्यूटीफुल माइंड क्लासेस। आज का हमारा टॉपिक है मोनोटोनिक सीक्वेंसेस एंड देयर कन्वर्जेंस। सो कम टू द टॉपिक, वी हैव मोनोटोनिक सीक्वेंस। सो फर्स्ट ऑफ ऑल, मोनोटोनिक सीक्वेंस क्या होता है? As we know that sequence is a function of set of natural number, function of whose domain is set of natural number and codomain is set of real number. So real sequence is a sequence whose domain is set of natural number and codomain is set of real number. So we take input as positive integer, as natural numbers. So what is monotonic sequence? So a sequence which is either increasing or decreasing in nature. That is, when we put values as positive integers, suppose we have a sequence an and an is equal to f of n, है ना? So function of set of natural number. So when we input here some positive integer, if the nature of the sequence is increasing, that is the output we get is increasing order, like an is equal to n square. Okay, here we have a1 is equal to 1, a2 is equal to 2 square, a3 is equal to 3 square, and like this. So here we are we can see that we can observe that the value is always in increasing nature. So we say that this sequence is monotonic increasing sequence. And another example we have Sn is equal to 1 by n. Here we have S1 is equal to 1 by 1, S2 is equal to 1 by 2, S3 is equal to 1 by 3. So यहाँ पे हम जैसे जैसे सीक्वेंस में आगे बढ़ रहे हैं, सीक्वेंस में जो टर्म आ रही है, टर्म की वैल्यू डिक्रीज होती जा रही है. सो दिस इज मोनोटोनिक डिक्रीजिंग सीक्वेंस. So one type, that is monotonic increasing, another type, that is monotonic decreasing. So a sequence is said to be monotonic sequence if it is either monotonic increasing or monotonic decreasing. So in general, a sequence an is called monotonic increasing if an plus 1 is greater than or is equal to an for all n belongs to set of natural numbers. A sequence an is said to be called monotonic increasing if an plus 1 successive term is greater than or is equal to the present term for every n belongs to set of natural number. For example, sequence an given by an is equal to n, an is equal to n square, like this. And again we have n plus 1 by n. This is also a monotonic increasing sequence. Again we have sequence sequence an is called monotonic decreasing if an is greater than or is equal to an plus 1. That is, present term is greater than or is equal to the successive term for all n belongs to set of natural number. For example, sequence an given by an is equal to 1 by n or 1 by n square, 1 by n cube, like this. So these sequences are monotonic decreasing sequence, as we have already taken in the examples. So a sequence is called monotonic if the sequence is either monotonic increasing or monotonic decreasing. If if this equality is removed, then the sequence is called strictly increasing, and if the equality is removed, then the sequence is called strictly decreasing sequence. Now we have a point when monotonic sequence will converge or diverge. Our concern is what is the behavior of monotonic sequence. That is, if a sequence is monotonic, when the sequence will converge and when it will diverge. So we have two sequences, Fn is equal to 1 by n and Fn is equal to n square. It is monotonic increasing sequence, it is monotonic decreasing sequence, and we can observe that this sequence is divergent sequence, this sequence is convergent sequence. Then what are the conditions which a sequence must obey for its convergence? That is, अगर सीक्वेंस को कन्वर्ट करना है तो वो कौन सी कंडीशंस है जिनको उसको फॉलो करना पड़ेगा. So for that we have a very important theorem, very important theorem, that is known as monotone convergence theorem. This establishes the criteria for convergence of monotonic sequence. That is, this states that the necessary and sufficient condition for a monotonic sequence to be convergent is that it is bounded. That is a monotonic sequence is convergent if and only if it is bounded. मोनोटोनिक सीक्वेंस तभी कन्वर्ज करेगा अगर वो बाउंडेड होगा, और अगर वो बाउंडेड होगा तो कन्वर्जेंट होगा. So now we are going to prove that monotone convergence theorem. So condition is necessary. Proof. First of all, condition is necessary. That is, let An be a monotonic sequence which is convergent. Then we shall prove that sequence An is bounded also. ठीक है, हमें क्या गिवन है? हमें ये गिवन है कि ये मोनोटोनिक सीक्वेंस कैसा है, कन्वर्जेंट है. तो since the condition is necessary, that is, which condition is necessary for the convergence? That is, the sequence is bounded also. So we shall prove that the sequence is bounded also. So for that we shall use the definition of convergence. So what is the definition of convergence of sequence? Since An is convergent, this implies that for phi greater than 0 there exists a positive integer small m such that absolute value an minus L is the limit of sequence. Since sequence n is convergent to a real number L, this implies that for epsilon greater than 0, there exists positive integer m such that absolute value an minus L is less than epsilon for all n greater than or equal to m. This implies that if we open the mod, remove the mod, we have an lying between L plus epsilon, L minus epsilon for all n greater than or equals to m. This is equation number 1. So let small g is equal to minimum of L minus epsilon. Here we have shown that this inequality is valid only for an plus 1, an plus 2, an plus 3 and so on. We have not included the terms. कौन सी टर्म्स को हमने इंक्लूड नहीं किया इस इनइक्वालिटी में? a1, a2, a3, am minus 1. So we shall explicitly include those terms here, a1, a2, a3 dot dot am minus 1, because ये इन टर्म्स ने इस इनइक्वालिटी में पार्टिसिपेट ही नहीं किया. अगर ये सारे टर्म्स इस इनइक्वालिटी में पार्टिसिपेट कर लेते तो हमारा कहने का मतलब ये होता कि फॉर एवरी an lying between L minus epsilon and L plus epsilon, मतलब उसका लोअर बाउंड भी मिल गया, उसका अपर बाउंड भी मिल गया, so that each term of the sequence is bounded between L minus epsilon and L plus epsilon. But this is not done here because this inequality is only valid for n is equal to m, n is equal to m plus 1, n is equal to m plus 2 and so on. So for other terms we are considering two real numbers. Capital G is equal to maximum of L plus epsilon, a1, a2, a3 dot dot am minus 1. So this is 2. From 1 and 2, we observe that हमने क्या ऑब्जर्व किया है कि each term of the sequence is lying between small g and capital G, that is for all n belongs to set of natural number. This implies that sequence an is a bounded sequence. That is कि हमने क्या लिया था? We have considered that the given sequence is convergent sequence and we have proved that sequence is bounded. So this is the boundedness is the necessary condition for the convergence of a monotonic sequence. अगर sequence monotonic है, वो convergent है, तो necessarily that sequence must be a bounded sequence that we have proved here. Okay. Now we shall prove that boundedness is the sufficient condition for the monotonic sequence to be convergent. That is कि अगर जो है कोई monotonic sequence है वो bounded भी है given है तो फिर ये sufficient condition हो जाएगी उसके लिए कि वो convergent होगा. That we are going to prove here. Condition is sufficient. So here we can consider that let the monotonic sequence an is bounded We shall show that sequence an is convergent. हमें क्या गिवन है? हमें ये गिवन है कि सीक्वेंस मोनोटोनिक है और वो बाउंडेड है, तो हमें क्या प्रूव करना है कि वो कन्वर्जेंट होगा. सो मोनोटोनिक है, दैट मीन्स वो मोनोटोनिक इंक्रीजिंग भी हो सकता है, मोनोटोनिक डिक्रीजिंग भी हो सकता है. तो वो मोनोटोनिक इंक्रीजिंग भी हो सकता है, मोनोटोनिक डिक्रीजिंग भी हो सकता है, बट अगर बाउंडेड है तो एवरी केस में वो कन्वर्जेंट होगा, ये हमें प्रूव करना है. तो हम एक कंडीशन ले लेते हैं कि वो मोनोटोनिक इंक्रीजिंग है. So let sequence an be a monotonic increasing sequence. Okay. Now, since sequence an is bounded, then the range set capital S of sequence an is also a bounded set. This implies that by completeness property of real number, set capital R, there exists a positive integer a real number capital M, which is least upper bound or supremum of set S. That is, an is less than or is equal to capital M for all n belongs to set of natural. Now, for epsilon greater than 0, there exists a positive integer small m such that m minus epsilon is less than am. ये क्यों हुआ? क्योंकि since m minus epsilon is not an upper bound of set Fx, because m is smallest upper bound, m is supremum, so any real number less than m cannot be an upper bound. So since m minus epsilon is not an upper bound of set S, that means set S में कम से कम एक नंबर ऐसा एग्जिस्ट करेगा जो m माइनस एप्सिलॉन से बड़ा होगा. बट सीक्वेंस n कैसा है? मोनोटोनिक इंक्रीजिंग सीक्वेंस. बट सीक्वेंस n is monotonic increasing sequence. This implies that m minus epsilon is less than am is less than or is equal to an for all n greater than or is equal to m. This is the property of monotonic increasing sequence. Since n is greater than m, so an is always greater than or is equal to am. This is property of monotonic increasing sequence, and each an is less than m, capital M. This implies that capital M minus epsilon is less than am is less than capital M plus epsilon for all n greater than or equals to small n. This implies that am minus capital M is less, absolute value is less than epsilon for all n greater than or equals to m. This implies that by definition of convergence, sequence an is a convergent sequence and limit an is equal to m. So just we have proved that if a monotonic sequence is bounded, then it must be convergent. That means boundedness is the sufficient condition for convergence of a monotonic sequence. So this has been proved that a monotonic sequence is convergent if and only if it is bounded sequence. So we take some examples so that this concept is down to your minds. So now we have a sequence. So now we take, for example, let's consider a sequence. We consider a sequence an given by, defined by an is equal to 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon n plus 3 plus dot dot plus 1 upon n plus n. N belongs to set of natural numbers. So it can be seen that, it can be observed that by nth term this sequence is very complicated sequence. This is not defined by a single term. This is summation, and the nth term is summation of n terms. So analysis of for the convergence, that is if we go for the behavior of the sequence, that is whether the sequence is convergent or divergent. So by simple looking we cannot say whether the sequence is convergent or divergent. So इसलिए अगर हमें इस सीक्वेंस के बारे में कुछ डिसीजन लेना है, तो फिर अगर हम मोनोटोन कन्वर्जेंस थ्योरम अगर इस पर अप्लाई कर सके तो हम आसानी से कह सकते हैं कि सीक्वेंस कन्वर्ज करेगा या फिर कन्वर्ज नहीं करेगा. So now we check that whether the sequence is monotonic or not. Now an plus 1. So an plus 1 is 1 upon. So we replace n by n plus 1. So replace n by n plus 1. So here we have n plus 2, n plus 3, because we are replacing n by n plus 1. N plus 4 plus dot dot plus 1 upon 2n plus 2. Now an plus 1 minus an. So we can see here, no. So here we like this, no, not like this. We can simply calculate by looking this. So this term is cancelled by this term is cancelled by this, and so on. So what terms will remain here? 1 upon 2n plus 2 plus 1 upon 2n plus 1. 1 upon 2n cancel हो जाएगा, एंड यहां से क्या नहीं कैंसिल होगा, 1/n+1। ठीक, ये वाले इसको कैंसिल करने के लिए कोई टर्म नहीं है। एंड यहाँ पे कौन कौन सी टर्म बचेंगी आप देख सकते हैं, ये आएगा 2n, 1/2n+1, 1/2n+, ये टर्म्स। सो ये सारी टर्म्स कैंसिल हो जाएंगे, ये यहाँ तक बचेगा कौन, इसमें से 2 बचेगा और यहाँ से 1। सो an+1 माइनस an ये आएगा। एंड एज वी कैन ऑब्जर्व हियर, so this is 1/2n+2 minus 2/2n+2 plus 1/2n+1। so this is, है ना, अगर हम इसको यहाँ ले आए तो this is 1/2n+1 minus 1/2n+2। so friends, this is पॉजिटिव और नेगेटिव। ये पॉजिटिव नंबर है या फिर नेगेटिव, कैसे चेक करेंगे, जिसका डिनोमिनेटर ज्यादा होगा वो नंबर छोटा हो जाएगा, बिकॉज डिनोमिनेटर इसका ज्यादा है इसलिए नंबर छोटा है, ये नंबर बड़ा है। बिग नंबर में से स्मॉल नंबर को अगर हम सब्ट्रैक्ट करेंगे तो हमें क्या मिलेगा, पॉजिटिव नंबर मिलेगा। सो दिस इज अ पॉजिटिव रियल नंबर, दिस इज अ पॉजिटिव रियल नंबर that is greater than or equal to 0. So this implies that an+1 is greater than or equal to an for all n belongs to set of natural number. Also we have an is greater than or equal to 0 for all n belongs to set of natural number, and an is equal to 1/n+1. This term is very crucial here, very important term. n+2, n+3 बहुत इंपॉर्टेंट स्टेप है ये, प्लस 1/n+n। सो यहाँ पे हमें थोड़ा सा अप्रोक्सीमेशन यूज करना पड़ेगा, क्योंकि हमें ये दिखाना है, हमने एक चीज तो दिखा दिया, मोनोटोन कन्वर्जेंस थ्योरम का एक चीज कंप्लीट हो गया, ये सीक्वेंस कैसा है, मोनोटोनिक सीक्वेंस है। कैसा सीक्वेंस है ये, दिस इंप्लाइज दैट सीक्वेंस एन इज मोनोटोनिक इंक्रीजिंग, क्योंकि वैल्यू बढ़ाने पर सीक्वेंस की वैल्यू, टर्म की वैल्यू बढ़ रही है, तो सीक्वेंस इज मोनोटोनिक इंक्रीजिंग। दूसरी बात हमें एक प्रूफ कर देना है कि ये सीक्वेंस कैसा है, बाउंडेड सीक्वेंस भी है, मोनोटोनिक होने के साथ साथ कैसा है, बाउंडेड भी है। तो देखिए लेफ्ट हैंड साइड से तो बाउंडेड है ये 0 से, क्यों, आप देख सकते हैं हर एक नंबर कैसा है, पॉजिटिव है ना, तो इसका मतलब सीक्वेंस का हर एक टर्म 0 या 0 से बड़ा है ना, कोई भी नंबर 0, कोई भी टर्म जो है 0 से छोटा नहीं है, इसका मतलब an इज ग्रेटर देन और इक्वल टू 0 फॉर ऑल n। अब इस साइड तो हो गया कि जो है ये सीक्वेंस के सारे टर्म इधर लाई करते हैं, क्या इधर भी कोई ऐसा नंबर मिल सकता है जो ये कह सके सीक्वेंस के सारे टर्म यहाँ पे लाई करते हैं, दैट इज हमें यहाँ पे क्या चाहिए, एक के चाहिए। अगर ऐसी ये फुलफिल हो जाता है कि सीक्वेंस के सारे टर्म्स 0 और k के बीच में लाई करते हैं, तो हम ये कह पाएंगे कि सीक्वेंस कैसा है, बाउंडेड है। तो उसी प्रयास में उसी को हम ट्राई करते हैं कि क्या हमें ये k मिल पाएगा ऐसा, तो उसके लिए हम थोड़ा सा अप्रोक्सीमेशन यूज कर रहे हैं। आप देख सकते हैं कि हर एक टर्म, जो सीक्वेंस का हर एक टर्म है वो किससे छोटा है, वो छोटा है 1/n से, क्योंकि n is less than n+1, n is less than n+2, n is less than n+3. So 1/n is always greater than 1/n+1, 1/n+2. So 1/n plus 1/n plus 1/n plus dot n times. This is equal to n/n. This is equal to 1. This implies that an is less than 1 for all n belongs to set of Convergent. Okay, so that means that this implies that sequence an, each term of sequence an is greater than 0 लेस देन 1, है ना। हमें क्या मिल गया, यहाँ पे 1 मिल गया। दैट इज सीक्वेंस का हर एक टर्म 0 और 1 के बीच में लाई कर रहा है। इसका मतलब क्या है, दिस इंप्लाइज दैट सीक्वेंस an is a bounded sequence, also it is monotonic, increasing. This implies that by monotone convergence theorem, sequence an is convergent. Okay? This is an application of monotone convergence theorem. जो हमने जो सीक्वेंस लिया था उसको हम सिंपली ऑब्जर्व करके ये नहीं बता सकते थे। इस सीक्वेंस के लिए हम ये नहीं कह सकते कि ये जो है कैसा सीक्वेंस होगा अगर हम सिंपली ऑब्जर्व करना चाहेंगे तो। बट अगर हमने मोनोटोनिक कन्वर्जेंस थ्योरम अप्लाई किया है, दैट इज once we have proved that sequence is monotonic and it is bounded, then by monotone convergence theorem it is convergent sequence. Friends, like, subscribe and comment my video, and if you have any queries, questions, you can ask me in comment section.